All right. So today we are looking at derivatives of exponential functions. First, let's recall some of the basic properties of exponential functions. Usually, an exponential function has the form, let's write, has the form f of x equal to a multiplying b to the power x. So that is the form of an exponential, functions, where we claim that a is the initial number, initial value. The b, we claim that is the base, okay, is the base. So let me write it for, and then the x as the exponent. So this is a general form of an exponential function, okay. But then we often, encounter the special exponential function. So we more often than not encounter the special exponential function. So the special exponential function is always is f of x equal to x e to the power x. So usually we call this one the special exponential function. Also want to kind of mention that the e is the Euler's value. Okay, so the e is called the Euler's value, and it's approximately, let me use this, and the e is approximately 2.71828 is what we call the Euler's value, and that's it value. Okay, good. So I want us to kind of take note. But today I want us to look at, shift our mindset from this to how best we can find its derivative. Okay, good. And we made mention of the fact that when we talk of derivative, it's about how a function is changing at a point. Okay, or how the function changes as a result of a change in its input. I want us to kind of, take note. All right. So the first thing I want us to talk about is that the derivative. So I would say that the derivative of the special exponential function, so the derivative of the special exponential function e to the power x is x. Okay. And I also want to mention that one of the most powerful functions in mathematics is the exponential function. One of the most important, the most relevant, functions in mathematics is the exponential function. So I want us to take note. And we claim that the derivative, the special exponential function e to the power x is itself, okay, it's e to the power x. So please, let's take note of this. This is a very powerful theorem. So please, let's take note. So if that's the case, let's look at some few examples and see how best we would appreciate this. So if I give you, so if I ask you to find, let's say, changing y with respect to changing x, for let's say y equal to maybe 3 e to the power x, and then the b part we have, maybe let's say y equal to x to the power 2 e to the power x. How do we find this? So let's see how best we can solve this. All right, how do you solve this? So if I have the first part, if I have y equal to 3 multiplying e to the power x, so we're going to find changing y with respect to changing x. So in that case, you're going to have what? By applying dy dx on both sides, or by applying derivative on both sides, you're going to have, so 3 is just a constant, okay? And since it's just a constant, you can just pull it out. But then we claim that the derivative of e to the power x is itself, right? So in that case, you're going to have 3 multiplying e to the power x. So take notes of that. All right. So what about the b? So what about the b? The b, we have y equal to x to the power 2 multiplying e to the power x. How do you find the dy dx of this function? So by applying derivative on both sides, we should have, so let's have derivative on both sides. Good. Now, this is more or less like a product of two functions. So since we have the product of two functions and want to find a derivative, what it means is that you just have to rely on the theorem that has to do with product of functions, right? So what we can do is that we have two functions. So if you recall, in previous videos, we talk about the product rule, okay? So we can cover one of the functions, then we differentiate the other. So what I do is I can decide to cover the x to the power 2. It's as if I'm being blind to x of x to the power 2, okay? So in that case, I'll put it outside here and then differentiate e to the power x, okay? Then since you're talking about product, we introduce plus, okay? Because we said that product always means addition. And then the next one, since first I covered x to the power 2, the next round, what I'll do is that I'm going to be blind to e to the power x, okay? I'm going to be blind to e to the power x and then differentiate x. So we have something like this. Good. So our next step, what we do is that now we are going to differentiate. What is the derivative of e to the power x? And that is itself. We said that the derivative of the special exponential function e to the power x is always itself. Okay, good. And then we're going to have what is x to the power 2. So we drop the power. Okay, so we drop the power, then we decrease the power by 1. Okay, which becomes x to the power 2 minus 1, and that is what x, right? So this is our results for this particular problem. I hope we all get it. All right, let's take notes of that. Now, what if, now the question is, what if I give you this problem to solve? Let me kind of give you a problem like this let's see how it goes. I think, okay, so I want us to look at a very important thing that I would want us to take note as well. So what if I give you, what then becomes the case for finding the derivative e to the power, let's say e to the power of e to the power f of x, and where f of x is also a function. Okay, if I give you this to solve, if I give you such problem, how do we approach such problems? If there's a problem that has a form as this, so e to the power another function, how do we do that? So there's a technique that we employ in order to solve such a problem. Okay, so how do we do that? So what we do is that we maintain the problem we are being given to solve. So we will maintain the problem. Okay, then we multiply the problem by the derivative. We multiply by the derivative of the power. Okay, is that okay? So this can also be written as what, e to the power f of x multiplying, and the derivative of f of x is the same as what, f prime of x. Okay. So let's take note of this. So over here we claim that the derivative of e to some power is the product of e to that power and then the derivative of the power. Okay. So I want that to take note. Very, very, very important. So if that's the case, if I give you an example as this, how do we approach it? How do we approach such an example? Suppose y equal to, like I say that, so I would say find dy dx, or change the y with respect to changing x for the case y equal to e to the power 8x, and then the b part y equal to e to the power minus x squared plus 4x minus 7, and then c y equal to e to the power root of x squared minus 3. How do we solve such problems? All right. The first problem, we have a problem as this. Y equal to e to the power 8x. Okay. So what we do is that we take the derivative on both sides. So by taking the derivative of on both sides, okay. Now how do we differentiate this? So what we said is that, so we said that the derivative of such problem, what is that we maintain the problem. Okay, so we maintain the problem. So we maintain the problem. We multiply by the derivative of the power of the exponent. Okay, good. The power of the exponent. In that case, you're gonna have 8, something like this. Okay, 8x. Then what is the derivative of 8x? And that gives us 8. So in that case, you multiply that and that gives us a result as this. I hope we are okay. So if you have any questions, please put it in the comment section. I would attend to you. And at this point, you have not subscribed, please subscribe, like, comment, and share this, relevant content to your colleagues and loved ones. Now, the B part, how do we approach the B part? So with the B part, we have y equal to e to the power minus x squared plus 4x minus 7. How do we do that? How do we find the derivative of this? So we claim that we take the derivative on both sides. Okay, so we take the derivative on both sides. Okay, and then we said that to solve this, what we do is that, so we maintain the problem. Then we multiply it by the derivative of the power. Okay, or by the derivative of the exponent. And the exponent in this case is what? Minus s squared plus 4x minus 7. Good. Now, what's the derivative of the exponent? So the derivative of the exponent, you're going to have what? Minus 2x plus what? Plus 4. Then we multiply the result by the outside. Okay, good. So that is it for the problem. So now you've solved the problem, so simple as that. And I should say that this is, as I keep mentioning, this is one of the most important, functions in mathematics. That's exponential functions. We don't play with exponential functions because exponential functions is used in finance, is used in biology, is used in in modeling infectious diseases, which is my specialty. We also use it to kind of quantities, grow rapidly, such as compound interest, population growth, or even the spread of disease like COVID. With the measures of COVID-19, mathematicians were the front of shaping the various numbers that one of the functions that they kind of use was the exponential function. So I want us to kind of take note. It's a very important, function. So I want us to please take note of that. Now, for the last problem, I want you to solve it by yourself, then put it in the comment section, then I'll answer you. So the last problem, I want you to solve it by yourself. But what if I give you a problem as this to solve? What if last week we look at the derivative of higher orders? That's what we did last week. But I want us to kind of use that idea to sort of solve a problem as this, and let's see how it goes. Okay. So if I ask you to find the second derivative for y equal to e to the power minus 5x to the power 2, how do we solve such a problem? So what we do is that we kind of we apply derivative on both sides. In that case, we're going to have so what we do is that we first have to find it, since we want to find the second derivative of this function. So first we need to find the first derivative, then we go further to find its second derivative. Okay, all right. So by using the chain rule, we first find the dy dx. Okay, so by using the chain rule, we first find the dy dx. So in that case, we claim that we kind of maintain the problem. Since this is an exponential function, we claim that we maintain the function, then we find the derivative of the exponent. And the exponent in this case is what is minus 5x to the power 2, right? And then when we differentiate that, we're going to have what? When we differentiate minus 5x to the power 2, we're going to have what? Minus 10x. Then we multiply it by what is outside, okay? Good. So this becomes our first derivative. Now, what then happens to the second derivative? So with the second derivative, we are going to use the first derivative, okay? We're going to differentiate the first derivative. And over here, there's something here. We can see that there are two functions. We have minus 10x, and then what another function? Another function is what? E to the power minus 5x to the power 2, okay? So product rule plays out here. So as I usually do, I do cover up. So first, what I'm going to do is that I'll cover the minus 10x, then I differentiate the exponential function, okay? So that's the trick we have been using. Since you're talking about product or multiplication, we use the addition. Then the next one, what we do is I will cover minus 10x, okay? In which case, this goes out, okay? Then when we differentiate e to the power minus 5x squared, what do we get? We claim that we differentiate the power, okay? So we differentiate the power, that gives us what? Minus 10x, then we multiply the result by the problem itself. Okay, and then when we differentiate minus 10x, what do we get? Minus 10. Then we multiply by what is outside. So let's take notes. So this is going to be our results for this particular problem. But then you can go further to kind of simplify this, and that will be all. So at this point, I want us to look at some of the applications of the exponential functions. As I mentioned, exponential function is one of the most important functions in mathematics. Today, I want us to look at how the banking industry sort of leverage the notion, the concept of the exponential functions. So the problem is that we want to know the value of the account after several years, and we are very fortunate that the function or the account, the value account is expressed in function. Okay, it's expressed in exponential functions. So I want us to kind of take note, which is related to the form of an exponential function, something like this. Okay, good. So I want us to please take notes. Very good. All right. So we considered Franco's Efficient Emporium invested $50,000 in an account that earns 1.25% annual interest, compounded continuously. Now the value of the account after 2 years is being given by this exponential function. Now, how do we find the value of the account after 5 years and the rate at which this particular account is changing over time? Okay, good. This is a very important one. So the A part, so I'll call this one the A. So the A part is that, the A part is I want to find, so we are giving the function 50,000 multiplying the exponential function 0 e to the power 0.01 25t. Now, the question says that what is the value of the account after 5 years? So we could say the A of 5 means that my time is 5. So after 5 years, what is the value of it? After 5 years, what it means is that wherever I see t, I should just replace it by 5, okay? In which case, when you kind of use a calculator, it should be approximately 53,224.72, okay? So if you, what this problem is saying, if I invest 50,000 in my account that, sort of earns 1.25% annual interest that is also compounded continuously, then the value of this account, which is expressed in this exponential function after 5 years, this is how much we'll get, okay? Now the B part is that we wanna, find the rate at which, so f prime of 5, for f prime of 5, what it means is that we want to find the rate at which, so f the a prime, the prime means that the rate at which the value of the account is changing. Okay. Now, for us to do that, what we do is that we first have to find the first derivative of the given function, right? We want to find the first derivative of the given function. All right. Now, what would be the derivative of the given function? So as we said, we maintain the given problem, okay? We maintain it, then we kind of multiply it by the derivative, okay? The derivative of the exponent of e, okay? So that becomes 0.0125c. Okay. So when we differentiate that, what do we get? So when we differentiate that, we should get, when we differentiate 0.0125t, we should get what? We should get 0.0125. Okay. Then we multiply it by what's outside. And when we do that, we should get 625. If you use a calculator, you should get something as this. So please, let's take notes. Now, what is the rate at which this particular function is changing over time? And the time is 5 years. So in 5 years, we would expect that this will grow by this amount, which would be equivalently 665.31. So over here, we claim that after exactly 5 years, this is how we can interpret this result. We'll say that after exactly 5 years, the value of Franco's, Station Emporium's account is 53,224.72. And at that instant, the value is growing at the rate of 665.31 per year. Okay. So this is how we can sort of, solve this problem. So at this point, please, if you have not subscribed, please kindly subscribe to my channel. Let's help this channel to grow. It's a new channel. Let's also, like, comment, share this content to your loved ones. Thank you for your time.